Hi there. In this video we're going to look at numerical methods and we're going to start with looking at how we can find roots and specifically how we can justify where a root is on our curve. So the first thing we need to ask ourselves is, what is a root? Well, a root is simply somewhere where our function crosses the x-axis. So if we look here, for example, this curve has three roots. It has this point here is a root, it has this point here is a root, and it has this point here is a root. Okay, so for this first bit we need to have a look and see what's actually happening to the curve close to this root. So if we zoom in on this point here, you'll notice that the curve to the left hand side of the root is below the x-axis, which means it's going to take a negative value, and the curve to the right of that point is above the x-axis, so that's going to take a positive value. So if we're looking for roots, if we're doing a search for roots, what we're looking for is where the curve goes from being negative to positive, or indeed from positive to negative. Now this only works on certain functions, okay? This only works on continuous functions. So on continuous functions, if f of a is less than 0 and f of b is greater than 0, then there's some number, let's call it c, and then there is a value c where a is less than c is less than b, so c is between a and b, and f of c is equal to 0. Now this actually has a very special name. This is called the intermediate value theorem, or the IVT, and it's something you'll go on to prove if you go and do analysis at university. We won't go into that here because it's a little bit beyond the scope of the course, not that it's a particularly tricky proof, and there's just a lot of foundational knowledge we need beforehand. Maybe I'll go through this at some point, but right now you just need to know that if a function is to the left of a point negative and to the right of the point positive, or vice versa, there is a root there. We do need to specify continuous, and I'll just show you at one point where this breaks down. So if we look at the line y equals 1 over x, for example, we get this situation. Now the curve here is negative, the curve here is positive, but there isn't actually a root in between those points because the line jumps down here to up here. There's a gap in the line, which in very simplistic terms is what it means, or is not what it means for it to be continuous. If there's a gap in your line, it's not continuous, this won't work. But generally speaking, we can find our roots by searching for these changes of signs. Okay, so let's look at an example of how to apply this and how to find whereabouts roots are. So we've got this function, x cubed minus 2x plus 1, and I need to show that one root lies in the interval minus 2, minus 1. So the way we're going to do that is, just a little bit of notation here, this interval minus 2, minus 1, this just means is in between minus 2 and minus 1. Now the square brackets mean they can equal minus 2 and minus 1, but it's not very likely that it will in this case, because it's likely to be a decimal if they're asking you this question. But we can certainly show this is the case, and remember we need to look for a change of sign. We need to look for the function going from positive to negative, crossing that x-axis. So first thing we're going to work out is we're going to work out f of minus 2. Now that is equal to f of minus 2, that's equal to minus 2 cubed minus 2 lots of minus 2 plus 1. Well, minus 2 cubed is minus 8. Minus 2 times minus 2 is positive 4. Plus 1 is minus 3. Similarly, let's work out f of -1. So that's equal to -1 cubed minus 2 lots of -1 plus the 1 again. -1 cubed is -1, minus 2 times -1 is positive 2, and then plus the 1, that gives me positive 2. Now the curve has gone from being negative to positive, so there's been a change of sign. So the root is between, or is in the interval, -2, -1. Easy as that. Okay, so on to part B. So we need to show that a different root is at x equals 0.618, accurate to 3 decimal places. Now this one's slightly less obvious what we need to do because we're not given an interval, or at least we're not given one explicitly. We are given an interval, it's just a little bit hidden in some of this information here. So can you think how we might be able to turn this information into an interval? Exactly, we need to write our error interval for x, and that's going to give us a range of values that we can check. So if x is 0.618 to 3 decimal places, well, what's the smallest it could possibly be? Exactly, so we get 0.6175 is the smallest it can be, because that or higher is going to round up to 0.618 to 3 decimal places, and similarly the upper bound is 0.6185. Notice the difference in the inequalities here. This one isn't a strict inequality and this one is. But now we have our interval, so what we need to do is, same as before, we find f of our lower bound, 0.6175. Now obviously not going to do this by hand, we'll do this in our calculators, so that gives us about 4.6 times by 10 to the 4. Really small, we'd expect it to be quite small, it's to 3 decimal places, but most importantly that is still positive. And similarly we find f of 0.6185, which if we plug that into our calculators gives us a value of minus 4.0 times 10 to the minus 4. Okay, so as you'll see again, there's a sign change. So x is in the interval 0.6175, 0.6185, which means x is equal to 0.618 to 3 decimal places. Just a little bit of notation here. I'm going to use a rounded bracket there just because this is a strict inequality, and this rounded bracket means that it can't be equal to 0.618. Brilliant.